Chapter 3, Exercise 9. Discuss the result of replacing the union operation by the intersection operation in the preceding problem. Now, if you didn't watch the preceding problem, or you forgot by now, it's okay. Let me rewrite it for you. The preceding problem, problem 8, was to show that the domain of the union of A is equal to the union of the domain of R, such that R is in A, and do the same thing for the ranges. Okay. So what this question is asking us to do is to determine whether domain of the intersection of A is equal to the intersection of the domain of R, such that R is in A. And similarly, is the range of the intersection of A equal to the intersection of the ranges of every R in A. Now, I must preface this video saying that I am not too confident about my answer. I don't see any obvious mistakes in my reasoning, but I do think that the end result is a little too nice for me to feel comfortable about it. And since there's no real indication in the problem statement about which way this should go, then I'm not entirely certain. But I will do my best to justify why I believe that these indeed are equal. So let's get started. Let's start with the domain of the intersection of A. So let me show you why I believe that this is true. By the way, if you disagree or if you know that this is wrong, please write it in the comments. So let's do the first subset. Let's suppose X is in the domain of the intersection of A, right? Then then we have two facts. We know that X is in the union of the intersection of A, and there exists some Y in the union of the intersection of A, such that X comma Y is in the intersection of A. So far, so good. Now, since X comma Y is in the intersection of A, we know that for all R in A, X comma Y has to be in R. Right? Now, what does this tell us? We know, and I showed this in the previous video, that if X comma Y is in R, implies that X is in the union of R, and X comma Y is in the union of R as well, which itself implies that X is in the union of R, and Y is in the union of R. All this to say that X is in the union of R, and there exists some Y in the union of R, such that X comma Y is in R for all R in R set A. Okay, so what does this mean? This means that for all R in A, X is in the domain of R. Thus, X has to be in the intersection of all these domains. So the domain of the union of A must be a subset of, the intersection of A has to be a subset of the intersection of the domain of R, such that R is in A. Right, so far so good. I hope no one has any objections so far. If you do, please voice them in the comments. Now, suppose X is in the intersection of these domains instead. Then, for all R in A, we know that X is in the domain of R. Right? So far so good. So what now? So X has to be in the union of R, and there must exist some Y in the union of R, such that X, Y is in R for all R in A. So for all R in A, just reiterating, X, Y is in R, meaning that X, Y has to be in the intersection of A. Okay. Thus, now, X, Y being in the intersection of A implies that X is going to be in the union of the intersection of A, and Y is in the union of the intersection of A. So X is in the union of the intersection of A, and there exists some Y in the union of the intersection of A, such that my hand hurts. X, Y is in the intersection of A. Thus, X has to be in the domain of the intersection of A. So the intersection of the domains is a subset of the domain of the intersection. So we conclude that that the domain of the intersection of A is equal to the intersection of all these domains. All right, that's my proof for why at least this one right here at the top is indeed true. So it checks out. Put a little check mark there. Now the question is, does the same thing hold for the ranges? Now, at this point of the video, you're probably saying, well, the proof is going to be pretty much the exact same. So yes, that's what I would say too. So yeah, I don't see why this would change at all. And I mean, intuitively, it makes sense to me that this is true, but it's still, I don't know, there's some ambiguity there that maybe I did something wrong here, but I don't see it. So I'm just gonna ignore it and keep going, as we usually do. So now let's do part B, where we show that the range of the intersection of A is equal to the intersection of all these ranges And for that, we must start first by showing that one is a subset of the other. Okay, now suppose y is in the range of the intersection of A, then y must be in the union of the intersection of A, and there must exist some x in the union of the intersection of A such that x comma y is in the intersection of A. Now x comma y being in the intersection of A implies that for all r in A, x comma y is in R. Thus, I'm just going to skip right to it. For all r in A, y has to be in the range of R. Thus, y has to be in the intersection of the range of R such that R is in A. There you have it. Next, alright. So, the range, the intersection of A, has to be a subset of the intersection of the range of R. So R is in A. There, okay. Maybe this was a bit of a jump right here from this line to this line. Let me see. You know what? I'll just do it once. Why not? I feel like I do this every video where I'm like, oh, I'm just going to skip it, and then I end up going back anyways, but whatever. So y is in the union of R, and there exists some x in the union of R such that x comma y is in R. Thus, y is in the range of R for any arbitrary R. And note that these two are the same thing, just expressed differently. I like rewriting things to be more legible either by humans or by, logical notation. It helps me to see both versions of the same statement sometimes. Now we're going to show that the intersection of the range of R such that R is in A is also a subset of the range of the intersection of A. So suppose y is in this intersection. Then for all r in A, y is in the range of R. Now this means that for all r in A, y is in the union of A, and there exists some x in the union of R, such that x comma y is in R. Now, if for all r in A, x comma y is in R, then x comma y has to be in the intersection of A. So x is in the union of the intersection of A, and more importantly, y has to be in the union of the intersection of A. This means that y is in the union of the intersection of A, and there exists some x in the union of the intersection of A, such that x comma y is in the intersection of A. Thus, y has to be in the range of the intersection of A. And it follows that the intersection of the set of the ranges is a subset of the range of the intersection. And now we conclude, as usual, that the range of the intersection of A is equal to the intersection of the range of R, such that R is in A. And there you have it. That is my justification. It is pretty much a copy and paste of the previous proof. You only swap out the the existential quantifier, that is the upside down A. No, the existential quantifier, that is the backwards E, for the universal quantifier, which is the upside down A. And things work out. They don't usually do. It's not often the case that if you swap out one quantifier for the other, things just end up working out. I know that quite well. In this case, though, I genuinely don't see how this doesn't go through. Like, no, someone should reject this proof. I feel like we just stuck to the definitions and things just happened to work out. Maybe that's why Enderton wanted us to discuss it. It is pretty cryptic what he meant by discuss the result of replacing the union operation by the intersection operation in the preceding problem. But who knows? Who knows? Mathematicians be weird like that. I mean, the man did write a whole text on set theory. So something's not right with him. And something's not right with me for doing these exercises on my free time. But here we are. At least what I can do today is this. I can put a blue check mark over this equality sign and feel happy about myself because I did some math. That's all that matters. Right. I hope this was helpful, and I'll see you in the next video. Bye-bye.